We've seen that any m by n real matrix allows us to express Rn as a direct sum of row of A and n of A, the row space of A and the null space of A. We know that the row space and null space are mutually orthogonal. And the fact that this is a direct sum comes from the fact that any vector v in Rn can be expressed uniquely as a sum of v row plus vn, where v row is some unique vector in the row space, and vn is some unique vector in the null space. Similarly, well, if U is a sum of the same VP with some other vector in the null space, and we'll call that other vector V sub n prime, then U is not equal to V because this is a unique sum. But all three of these vectors, VP itself, V, and U, all map to the same vector in Rm. And the reason for that is very simple. If we apply the transformation to Vp plus Vm, the transformation is linear, we get T of Vp plus T of Vn. Well, the transformation applied to Vn is just what you get when you multiply A by Vn. Vn is in the null space of A, so T of Vn is going to be 0, and you're just left with T of V row. So that this vector has to map to the same place as V row. And that's something we established a long time ago. And of course the same is going to be true for U, because V row is going to map to the same, to whatever V row maps to, and Vn prime being in the null space will map to 0. So you're just going to get the same thing. Okay. Well, the main idea here then that I want to develop though is that Rn is the direct sum of its row space and its null space. In a similar manner, Rm, now A can be, Rm, A transpose is an n by m real matrix. This is Rm. That means, in the same way, with all the same arguments, totally irrelevant to anything that happens over here, A transpose is a mapping from Rm to Rn. It's got a row space, and it's got a null space. Didn't leave myself much room to write my null space, but here's the null space of A transpose. Okay, this null space, again, well, Rm, I write it up here. A transpose is a mapping from Rm to Rn, and just from that, and from what any matrix does to the space when you define the transformation, Rm is a direct sum of the row space of A transpose and the null space of A transpose. So, very important addition to the picture, and I'll write that relationship didn't leave myself room to write it in one line, but okay, now there's much more that we can say about this subspace, but these are the four fundamental subspaces. So these are the four fundamental subspaces of the transformation T, where again T is a transformation such that T applied to V is just what you get when you multiply the matrix A by the vector V.